Excellent. Welcome, everybody. Thanks for joining. Thanks for joining us today in this webinar about quantum computing, brought to you by ParityQC, Exoscale, and Vision. My name is Adrian Kosmaczewski. I'm developer relations at Vision, the DevOps company in Zurich. And today we have a pan-European event for you. We've got the Exoscale team in Germany, the ParityQC team in Austria, the Exoscale team in Switzerland and Germany, the ParityQC team in Austria, and Vision in Zurich. So I'm speaking to you from Zurich today. I'm thrilled to have you here on stage, and with me we have Magdalena Hauser and Wolfgang Lechner from ParityQC, from Exoscale, Nicole Voigt and Sebastian Pité, and from Vision there's myself, Adrian Kosmaczewski, and Arno Aukia, who I forgot to mention on the slide. Basically, the workings of this webinar are very simple. We are going to have a 30-minute presentation, 40-minute presentation from ParityQC about the subject of quantum computing. And afterwards, we're going to have the opportunity to have some questions answered, because I'm pretty sure you have plenty of questions about the subject. It's a very mysterious subject, at least for me. So I'm very curious to see what we're going to learn today. There's a Q&A box on the bottom side of your screen, or yes, it should be on the bottom side of your Zoom screen. So feel free to post your questions there. And at the end of the event, Magdalena and Wolfgang will answer those questions for you. So without further ado, please, I give you here the screen, Magdalena, and Wolfgang, please feel free to share your slides. And thank you so much, everyone, for attending.
Hello, everyone. Wait a second. I hope you can see this.
Okay. Perfectly well, yes.
Should I start? So yeah, thanks very much for giving us the opportunity to give this webinar here. So we're very excited to speak about our software solution and our architecture solution for quantum computers, which will be available via Exoscale. And maybe to introduce ourselves, Magdalena, do you want to start?
Sure. So hello, everybody. My name is Magdalena Hauser, and together with Wolfgang, we are co-founders and co-CEOs of ParityQC. You might wonder why we appear, the both of us, but it is actually our core philosophy to appear as a team and do everything as a team, as well as with our team in the background. This is how we run our company.
Exactly. And my name is Wolfgang Lechner. I'm a professor at the University of Innsbruck, and together we founded this company. So today we want to speak about solving optimization problems on quantum computers. We want to motivate why this is important, why this will change the future, why now is the time to actually try it out. And we will show how to do this with our solution. So let's start with a very brief introduction on what is quantum computing, and a little bit what are the options that we have at the moment and what the status quo is. Classical computers work on bits, which are 0 and 1, and quantum computers also work on bits, but quantum bits. And the way to think about quantum bits as opposed to classical bits is that the classical bits are still hidden in the quantum bits. They are visualized here as dots on the right-hand side. But the difference now is that there's not just these 2 points, but the actual magic behind it is that these quantum bits are north and south poles of a sphere. So this can be really imagined like like a sphere where every point on the surface is accessible. So just like on the equator or on the poles or anywhere in between. And now this means because these are quantum bits, so this is the so-called Bloch sphere. These qubits can now be, for example, in a superposition, which means that the bits can be in position 1 or in position 2 at the same time. And this is already the first counterintuitive thing, because we say they are 0 and 1 at the same time. This is really a quantum effect which has no classical correspondence. And it's also a bit there is no real words for it, because at the same time is also kind of the wrong word, because it has nothing to do with time. So one should really think about it as a state, or as a single state, which contains 0 and 1 at the same instance or the same way. Then the second remarkable quantum effect is so-called entanglement. So I'm sure you also heard about this. This is if there is more than one qubit, so if there's 2 qubits, for example, then they can be in an entangled state, which means is that, for example, if one qubit is in state 1, then entanglement can mean that the other one has to be in state 0. And the third quantum effect that has no classical correspondence is the so-called tunneling effect. What this means is that if you think about a classical system, for example, a mountain scape or mountains or valleys, then if you want to go from one valley into the other valley, you have to climb over the mountain. And this is something that happens in many algorithms. For example, if you have optimization problems, then these mountain ranges and valleys would be so-called local minimas, and you would like to go from one local minima to another. And in quantum mechanics, you can do what is called tunneling, which means is you don't have to go over the full mountain range, but you can go through the mountains. And all these 3 aspects is something that we want to make use of as a resource. And that is what quantum computing is. The output of this is that if you think about classical methods to solve problems, then we have certain complexity classes in computer science, and the hardest one is the so-called NP-complete problems or NP-hard problems, which means that by adding one constituent, the problem has exponentially longer runtime. And this is something that is unavoidable, so classical algorithms can be improved, but they cannot be improved to a polynomial scaling in these NP-hard problems. And quantum computers can do this for certain classes of problems. For example, integer partition is something where we expect an exponential speedup compared to any classical algorithm, which will really disrupt many fields in computer science, for example, cryptography. And for optimization problems, we can enhance them in a polynomial way. And this is also quite remarkable, because if you think about polynomial enhancement of such important algorithms as optimization, will have an even larger impact. Just think about Fourier transform and fast Fourier transform. Fast Fourier transform has a quadratic speedup to Fourier transform, but it actually started the whole information area. As I mentioned, in quantum computing means that we make use of quantum effects, entanglement, superposition, and measurement as a resource. So we are using them already in our daily lives, but for computing, we want to make use of them as a resource. And the field is currently divided into 2 main directions. One is the so-called universal quantum computer. What this means is that we build a device which can solve any problem. So this means we really follow the approach of classical computers, which means we have gates, we have universal sets of gates. And with these universal sets of gates, we can make them programming languages. And these programming languages are really the sequence of the gates. And this means we need compilers, we need languages that allow us to encode the problems, and we need the hardware to do this. And this is somehow the dream from the 90s a bit. So 1990s, this was the big goal of building a universal quantum computer, and this is still one of the big goals. But it's also one of these goals that gets further apart the closer you get to it. So we are working on this now since centuries and since decades. And this is something that is still not realized. And that's why currently the big trend or the big new direction is to actually find algorithms or quantum ways to use quantum mechanics to do computation in the so-called near term, so with devices that are available. And what this means is that, this is something that we basically do in our company and in our research group, that we completely forget what has been done on this universal quantum computing, and we really rethink quantum computing in a way with, okay, what do we have available and what can we do with it now? And one outcome of this was, for example, the so-called one-way quantum computing, which is a completely new way to do quantum computing based on measurements. And this is something that has currently a huge revival with photonic systems. And there is what is called adiabatic quantum computing. This was our first contribution to the field. This is a method where we basically use Hamiltonian dynamics. So Hamiltonian dynamics means that we use a physical system which we build to solve a problem, a numerical problem. So this can be, the analogy would be a mechanical calculator from the 19th century, where we basically in the hardware encode the optimization problem. And the third category is, or the second category in this sense, is quantum simulation. So here the idea is that we don't solve really a numerical problem, but we solve a physical problem. So use a physical device to solve another physical problem. And this is also something that currently has a huge revival due to material science, which can be strongly enhanced with these methods. And with this, I would like to hand over to Magdalena to tell you a bit about the applications of all this.
So why do we think that quantum computers are important? So we do think that quantum computers will be a disruptive key technology in many, many fields. So when you think about cryptography, or as we said, optimization problems, and we define, by the way, optimization problems as one field that spans over all these categories. So machine learning also could be an optimization problem, as well as material science or material simulation. And when you think about the applications of these technologies, think about all the core aspects of our society that surrounds us. For example, mobility. So if you think about traffic routing, or how to produce cars more efficiently, or if you think about cybersecurity, we hear a lot about this quantum computing threat, where quantum computers will be able to solve any code that is current, or any cryptography that's currently out there. This might be a threat, but so just to comment a little bit, it's not going to be that dystopian future as we think about it. There will be post-quantum cryptography that's already been established. Then we have the health sector. So for example, if you think about protein folding, or how to efficiently develop new medicines, is also something where quantum computers could help. And as well, of course, the finance sector. They're always the first. If you can make money out of it, it's going to be the finance sector who will be the first to adapt it. And what we're going to show you in a bit is also the use cases that we already did in these fields. What all these fields have in common is that even small improvements already have an enormous impact on society. And we're going to tell you a little bit about what the status quo is at the moment with quantum computers all around the world. So we have this hardware race going on. Maybe you've heard about this, but at the moment it's in North America and in Europe and in Asia. There's a lot of development going on in the hardware sector. And the goal is to really solve an industry relevant problem on a quantum computer. So when we think about industry relevant problems, we do think about optimization problems. So that this will be the first problems that can be solved on a quantum computer. The problem is that at the moment, neither the hardware nor the software is in the state where this can be done efficiently or to really solve a problem that is big enough that it is industry relevant. What we do so we are a quantum architecture company who works together with hardware and software developers because we think that a quantum computer has to develop as a unity, so it can't be developed separately. But the problem at the moment is that no standards or APIs are defined already on how to, so we don't know actually how the perfect final quantum computer will look like. What we do know is that we have two kind of processes or aspects that are going to be followed at the moment. So we have the gate model on the one side and the annealing model on the other side. So these are two methods that quantum computers can be in. You may have heard of the Google chip. So this Google Sycamore chip that performed the Google supremacy experiment. And this supremacy experiment actually was a problem designed for the Google chip, but what it was very important that it showed that a quantum computer can potentially solve a problem better, faster, or more efficient than a classical computer. On the other hand, we have D-Wave. D-Wave does analog quantum computing or annealing. And D-Wave is especially good for solving combinatorial optimization problems. So this is another aspect. So these are more specialized devices. Gate models or Google, for example, they follow a more universal approach. And maybe, yeah, Wolfgang can tell a little bit about why we don't have a fully functional quantum computer yet.
Exactly. So we identified three challenges that have to be overcome in order to achieve quantum advantage. And the first one sounds almost like too obvious. It's of course scalability, but there is many aspects behind scalability on the hardware side. So in software, we know what scalability means, but in the interplay between hardware and software, this is actually quite a subtle thing. And one challenge, for example, is that if you build a certain quantum chip and then you make it larger, then you encounter a problem which is called crosstalk, which means that certain operations interact with other operations on your chip. And this is something that makes even current approaches non-scalable, because you have, so to say, random gates on your chip. The second big insight that we try to convince people about is that the real bottleneck in scaling up quantum chips is not so much the number of qubits, but the control of these qubits. So this means at the moment, the way quantum computers are built is that we build quantum chips and let them interact, and then the control electronic is, so to say, individually designed for each of these interactions. And this is something that has to change, and we think is the real bottleneck. And the third one is that algorithms somehow have to be able to hold the complexity of the problems that they want to solve. So this means there is a certain number of qubits which with a certain connectivity which is just required to solve certain problems. And for all these problems, you have a solution, and this is what we call this parity architecture. So our core our core technology in the company that we developed is, on the one hand, architecture for quantum computers. So this is really a blueprint on how you build quantum computers and how you connect them. And in addition to that, we have an operating system, which is called ParityOS, which allows one to make use of this architecture. So Magdalena will then tell a bit more about the operating system. I would start with the architecture. So what you see here on the left is literally everything that you need. So it's so simple that you can basically draw it with only two elements. The white dots are qubits. They are arranged on a chip, on a square lattice. And the red squares are the couplers between these chips. And they always connect 4 qubits. So these are so-called parity operations, which is operations between 4 qubits. And this is already an astonishing thing, because if you think about a classical computer, then everything is built on pair interactions. So, for example, AND gates or OR gates, or single operations like NOT gates and things like this. And quantum computers until now are also built like this. So people replaced the NOT gates by CNOT or by quantum NOT gates, the AND operations by quantum AND, the OR operations by quantum OR, and so on. In our case, there is no interactions between 2 qubits. There's always interactions between 4 qubits. So this means, and the second remarkable thing about this is that the interactions are completely independent of the problem. So this means there is no programming language which concerns the gate and the gate sequence, but the gates are always the same. The problem is fully encoded in local operations. And this allows one to build fully scalable quantum chips, because all the gates are always the same. They can be fully parallelized. And this means that we can eliminate this crosstalk problem that we talked beforehand. It also means that we can greatly reduce the complexity of the interactions, because we can do global gates. So it's an architecture that really influences the hardware stack, but also the full software stack. And ParityOS is the operating system which uses it then. And I think Magdalena would tell us a few words about it.
Yes. So everything we do is really complex. So in order to operate a quantum computer, you need a lot of knowledge on how to do this. So actually sending a problem to a quantum computer takes a lot of operations in between. And what we tried to do with, or what we did with ParityOS, was make the progress, or this whole process, as simple as possible for everybody to solve an optimization problem, for example, on a quantum computer. So what you see on the right side is how our ParityOS, in a very, very easy schematic way, how this works. So what you do is you put you have an optimization problem, a real world problem as input. The optimization problems go through our parity transformation. We have a compiler that really translates this to a language that the quantum computer can understand. And what we have at the last thing is this hardware design optimizer. So as I said before, we don't think that hardware and software should be developed independently, but we need to consider the hardware and the unique features of each hardware in our software as well. And this is what we do with our hardware design optimizer. So what you get out actually is a quantum algorithm that can be solved by a quantum computer. Our whole operating system, maybe this also differentiates ourselves from what you're used to classical computing, is that our operating system lives in the cloud. So it's not actually on a quantum computer, but can be accessed from everywhere via the cloud. And it works with every hardware. It works best with hardware that is built with our architecture, but it does work with others as well. So if you want to use ParityOS now, what do you have to do? It does look like a little bit complicated, but actually only need to send us one line of code. But this one line of code has to entail the whole optimization problem as a Hamiltonian. So if you know how to formulate in Hamiltonian, you're good to go. If not, this is something that a lot of people are working on, so you can work together with them and then send us your Hamiltonian. And what you get out is actually this quantum algorithm, which you can send to every quantum computer. So in the digital sense, it's a set of gates that has to be run on a quantum computer. In the analog sense, you get a driver Hamiltonian and a scheduling function. And both of these can be sent to quantum computers that you work with us or not. And when we say all platforms and methods, so when we talk about platforms, that's actually the tiny qubit and the material it is made of. So if we think about trapped ions, it's going to be an ion that is trapped, for example, done by IQ, AQT, or universal quantum, or electron. When we talk about atoms, it's something that Pascal and Paul Quantum, for example, work with. Then we have superconducting qubits. These are actually, this is the platform that's actually most advanced and most developed at the moment. All the big ones are going for this platform. So we have Google, IBM, Rigetti, D-Wave, NEC, for example, working with superconducting qubits. And then we have some platforms that need a little bit more development in order to achieve the same numbers as superconducting does at the moment. And this is NV centers or quantum dots. And all of them can be either digital or analog. And we could actually, so we do work with all of them. And now Wolfgang will tell you a little bit more about use cases that we've done before and where quantum computing is useful.
Yeah, so in case you're interested in working with us, let us show you some showcase use cases that we already worked out and used. So one is the so-called smart charging of electric vehicles. So this really should just serve as an example where you see where quantum computing can be used. So the idea is here that you have self-driving cars that drive themselves to a charging station. So this car still has a plug, which it probably cannot use itself, but maybe if somebody comes up with automatic charging methods. Anyways, so what we want to minimize is the total load of completion time and an optimal scheduling of the load times. And this was a project where we basically got exactly this information, and we came up with a way how to encode this on a quantum computer. This was a project together with Electrices de France and Pascal, which is also a French company based on atom quantum computer. And what we found was that with our compiler, we can get a scaling advantage compared to any other algorithm, and we can basically solve these problems. Now, just to get your expectations not too high, this is at the moment still done for toy models, which means we have 4 charging stations and 4 cars. However, this is something where we know how to scale up these things and how to calculate this on a quantum computer. Now, another use case that we recently worked on was in fintech. So this is, of course, an interesting area because there's a lot of optimization problems. And it also shows that optimization problems are not things where you optimize something, but in this case, you are so to say doing the opposite. You're looking for the worst case, in particular, predicting financial crashes. So the project was about having a system of companies where each company owns stock of each other company, which is by itself a stable system. But once there is rating companies, the system actually breaks down once rating companies influence the system. And this then leads to financial crashes. And this can be seen really as a mathematical transition from stable to unstable. And this is something that our architecture, for example, can encode on a quantum computer very efficiently. And the third one, that's quantum chemistry. So this was about finding the minimum or the electronic structure of molecules, which basically means you're minimizing the orbital energy of them. So this is how quantum chemistry can probably be summarized. And we did this for 2 different molecules, which are important for battery design. And we find also again that our architecture can very efficiently map these problems. Again, to keep your expectations where they should be. So the molecule on the left side is slightly more complicated than H2 and lithium. So let me just quickly say why ParityOS is at the moment very interesting for use cases and how to solve optimization problems with them. As Magdalena already mentioned, quantum computing is complicated and it's probably hard to get started with it. And that's more or less what our operating system should be. It should be a simple entrance for everybody to make use of quantum computers. So let me say as a very short tutorial which parts of the compilation you would basically be saved. So the example that we want to show is graph partitioning. So if you're a computer scientist, this is probably a problem that's very familiar with you. And we want to use this example to really guide you through how you would interact with us, given that you want to solve this problem, for example. So if you're a computer scientist, you would probably think about this problem as a pure graph problem. So you have a graph with vertices and edges. And the problem that you have to solve is written here as an English sentence. So what is the partition of the set V into two subsets of equal size, such that the number of edges connecting the two subsets is minimized? And I've already drawn the solution on the left side. So visually, you could imagine this as separating the graph into two pieces. So I indicated this with a line here. And all the red qubits will be in team red, and the green ones will be in team green. And graph partitioning basically means you have to split up your graph into in two teams, green and red, such that you minimize or that you cut the least number of lines connecting them. And the solution for this example is can be more or less already seen by just looking at the graph. However, once this is a non-trivial or non-planar graph, this is an NP-hard problem. So this is one of the famous NP-hard problems. And now there's, of course, classical algorithms for them, which are all exponential. And now, usually you would have to talk now with physicists in order to solve this on a quantum computer. And we want to spare you from talking to physicists. So what you can do with ParityOS is you can basically come from computer science and solve this problem. But let me just say what a physicist would do with this problem. A physicist would look at this problem and translate the mathematical cost function into an energy. This is always the strategy how to solve optimization problems on a quantum computer. So the idea is to translate it into a physical system, and instead of minimizing then some mathematical function, we are minimizing the energy. This is something that nature can do for us, and this means also a quantum computer can do for us. And what we would do is we would replace the nodes by bits and then later by quantum bits. And we always write them as sigmas. So, and the sigma can be either plus or minus 1. And the plus 1 would just mean it's team red, and the minus 1 would mean it's team green. And now you have to translate the sentence up there into mathematical formulas. And the sentence consists actually of two requirements. One is that the two subsets have to be of the same size, and the other one is that the connections should be minimal. And the first part of the sentence can then be formulated by an equation, which is just the sum of the sigmas to the squared. So if you think about this, you have two subsystems and they can be plus 1 or minus 1, which means if you sum up the plus ones and the minus ones, and they are equal size, then this will be exactly 0, which means if you square this, 0 is the absolute minimum that you can reach, which means that this part of the formula tells you that the two subsystems will be of equal size. And the second part is that the number of edges connecting the two subsystems are minimized. And this can again be written as an energy in the second part of this equation, which says 1 minus sigma I times sigma j half. So this means now we are not summing over the nodes, but we're summing over the edges, and we are looking at all connections. And if they are in the same team, then sigma I times sigma j would be always plus 1, because if they're in the same team, it's either minus 1 times 1 is 1 or plus 1 times plus 1, which is always plus 1, which means we have 1 minus 1, which is 0. And if they're in a different team, then this will be this product will be always minus 1, which means it says always then 2 divided by 2, which is always plus 1. So this means this term counts all the edges from nodes which are in two different teams. And by minimizing this energy, we are minimizing the actual mathematical problem. And what you can see now is that this always then translates. So if you write out all these sums, this always then translates into a problem which has the form which we've written down below. So this is products of qubits and sums of qubits. This is what comes out always in the end. And with our operating system, we are taking then this as the input. So this was shown here. We are taking this form written in this form as the input, then do all the transformation, all the compilation, all the hardware design, and what really comes out in the very end is a quantum algorithm to do this. So this means our solution at the moment allows one to take a use case, work it out with formulating it as a physical system, and then everything else is taken over by ParityOS. And once you have this algorithm, algorithm has then this meta language that Magdalena mentioned before, so it can be executed on any hardware. So for example, if your favorite hardware developer has atoms, it will be done on atoms. If it's superconducting, it will be done on superconducting. There can also be an iteration with us, so we actually know all the advantages of all these platforms. So we know where superconducting have their advantage, where atoms have their advantage. We have a connection to basically all these platforms. So we can also do then the real world test on these platforms. And we have what we call this plug-in system, which means that this last part, so the hardware optimization part, really takes into account hardware specific properties of hardware that exists. So for example, some quantum computers are very good at doing four-body interactions. Some are very good at C-NOT gates or quantum NOT gates. Some are good at other operations, and we can then actually select also the best hardware to solve this problem. Okay, so.
Yeah, so if we've sparked your interest or not confused you too much what quantum computing is about, you can send us an email and we can have a talk on how you can work with us. And I think Nicole Voigt from Exoscale will also explain how this OCRE network works and how you can work with us within this OCRE network. So if you have any questions, feel free to ask us. And thank you very much.
Thanks a lot, Magdalena and Wolfgang. It's been really, really interesting. And I cannot say that I understood everything, but it certainly looks amazing. So there's already a question. So I'm jumping directly to the Q&A section. And Baman Javadi is asking, what was the performance results of the use cases in comparison with the classical optimization, for example, time and throughput?
Yes, thank you very much. So this is, of course, a very important question. So currently, a quantum or on the classical side, there is for different problems, there's different ways how to solve them. We usually distinguish between the exact methods. So these are deterministic algorithms that give a certain performance. And for these kinds of optimization problems, the deterministic algorithms stop at around 100 nodes. So once you have 100 nodes, you cannot solve these problems on the best hardware. Now, the actual most powerful algorithms, however, are heuristics. So these are Monte Carlo methods or so-called parallel tempering methods, which basically means that you already do this physical trick that we mentioned for quantum computers also on the algorithmic side. So this means you translate your problem into an energy landscape, and then with Monte Carlo, you're sampling this landscape, or with parallel tempering, what you basically do is it already has the word temperature in it, no, so it's really a physical idea. So you treat the system at different temperatures and then find with this global minima. However, this is heuristics, which means that there is no guarantee that you have found a global minimum. It's something where you sample local minima. And so this makes the comparison then hard, because adiabatic quantum computing, for example, is something that guarantees for a global minimum. Now, this means this also means that you have to think, if you compare quantum and classical, what's actually what you want. No, do you, for example, do you really require a global minimum, or are you happy with some local minimum without knowing what the actual global minimum is? And there, quantum mechanics has also like an analogy to the hybrid methods, or to the heuristic methods, which are called quantum annealing and variational quantum optimization. So the idea is that, similarly to the classical algorithms where you sample and you don't guarantee for the global minimum, you can also do this on the quantum side. And for this, we know, for example, there is some highlight algorithms like the Grover algorithm. The Grover algorithm has mathematically proven quadratic speedup compared to any classical algorithm. What this means is that you have Grover is also a bit like a template algorithm for other algorithms. So what you can show is, or the original Grover algorithm was for searching in data. So this means you have unstructured data and you're looking for a certain piece of bits. Then this is something that can guarantee a quadratic speedup. And this is like a subroutine which you can use for optimization algorithms. Now, the downside, or the realistic way to think about it, is that these heuristic methods like Monte Carlo and parallel tempering are extremely powerful. So with these methods, you can solve problems up to 10,000 of nodes. Again, you don't guarantee for the minimum, but often you don't need the last 1%. So these are really super powerful methods. We have super powerful supercomputers which solve all these problems. However, with quantum computing, we can already get into this region with also having around 10,000 qubits, which means if we want to compare in the end these heuristic methods with classical heuristic methods, we can do this once we have 10,000 qubits, and this will be then also a reality test for real quantum computers. And throughput, just to also mention this, so one other big advantage of quantum computing is that there's an intrinsic parallelizability from using superpositions instead of serializing the data. So the dream of quantum computing is that you basically generate states which hold a lot of bits at the same time. So this means, instead of sequentially feeding data into your algorithms, you first design a quantum state which contains the information in a single state, and then does the calculation with basically a single state. This is a dream that's around for a long time. It turns out that preparing this initial state is almost as hard as just feeding it sequentially. So this means the big dream of having an exponential advantage in throughput is still a dream, but something that people are working on.
Excellent. Thanks a lot, Wolfgang. And there's another question from Martin Brake. He basically asks, what's the cost of all of this? It sounds wonderful, but what is the cost?
Do you mean the cost for our ParityOS, or for developing a quantum computer and run actually a problem on it? So the second one actually said building a quantum computer is very cost intense. Lots of big corporates like Google and Amazon and so on, they are spending billions on developing the next device. Also, governments all around the world spend a lot of money in order to develop a quantum computer. So building the hardware is very cost intense. What we try to do with Parity is actually being on the intermediate step between hardware and software. So we don't require this hard or this massive amount of capital that is needed, but profit either way, whatever hardware comes out at the end of it, at least if they work with our architecture. And what sort of cost is our ParityOS? So this is a very good question. So usually we work together with hardware developers. So they use our ParityOS and integrate it in their software stack. So we are paid by the hardware developers and they charge you for their time. So for Exoscale, we did an exception and for Vision and let you use it directly, as to say as an end user. And of course, if you're interested, you can just ask us and we can develop a price screen.
Excellent, thanks a lot. So I have a question that I thought during the presentation, because of course many companies are positioning themselves in this space because clearly there's a lot of promising results already available. There's a lot of research, a lot of money being poured. And I've heard about Amazon Bracket or Google Computing Service, Azure Quantum. There's Microsoft Q#, which is a programming language that allows you to somehow play with quantum computing concepts on your normal silicon-based von Neumann computer, right? So how does ParityOS compare to such initiatives? How do you compete or how do you collaborate with those? I'm curious about that.
You want to should I?
Yes.
No, okay. If we don't compete with them. That's the thing. Yeah. So this is the problem if you're a quantum software company at the moment. You have to compete with Google and Amazon, and every big quantum hardware developer has his own quantum hardware full stack. So for example, if you take Rigetti, they also have their own languages, PyQuil, they have Rigetti Forest. So they have this whole full stack. Google has its Cirque, Google has its own environment. Amazon Bracket, you already mentioned it. So this is why we really don't compete with them. It makes no sense. But this is why we are a quantum architecture company. So ParityOS is a tool in order to help everybody out there to also work with us and solve optimization problems efficiently. We do beat the best compiler out there at the moment. So this is one spec that we can get. But as we are a quantum architecture company, we work with hardware developers and are really on their side, not against them.
Perfect. Fantastic. That gives a little bit of a big picture for me. It's interesting to see how it all works, because of course I'm very new to the subject. We have another question from Barman Javadi. Could you please comment on the data intensive big data optimization? We are still generating all the data in analog or digital form. Do we have to translate that data into qubit? Is this a limitation? What could you answer?
Yeah, we are interested a lot in quantum machine learning. So we have patents on how to use our architecture for quantum machine learning. So this is a topic that's very close to our heart. And actually, there's many good questions in there. So let me start with the first one, this data intensity or big data. So my worry is that there is a certain overpromise on the connection between big data and quantum computing. As I mentioned before, often quantum computing is motivated by this aspect that you can store a lot of data at the same time in a few bits. However, this is only half true, because generating these states is extremely complicated. So it's at the moment we have no algorithm published which allows one to efficiently generate such a state. This is a big open question, and before we don't solve this, there is no way to somehow think about this big data in quantum. So at the moment, we are actually more interested in computationally hard problems. So for us, the ideal problem, or at least the way I think about these problems, is something that has very little input, very little output, but an enormous amount of possibilities in between. So these are more number crunching problems, like reversing hash functions of cryptocurrencies or something like this. So which are problems which have a few bits input, few bits output, but a lot of calculation in between. Then the preparation of the data, that's a second very good question. Because currently most people still think about quantum computers as digital devices. However, we are like designing quantum computers. No, we are not, as Magdalena mentioned several times, we're not software developers. So we are not just taking the status quo of gates and designing algorithms for this. We are always, with everything we do, we always go back to equation number 1 and rethink about everything. And this also means that if you do this, there is no real difference between analog and digital in quantum. The reason is that if you think about the stack, it looks a bit like this, that if you make your quantum device, then you come up with an algorithm which consists of digital methods. But then if you implement them in the lab, what you actually do is you have like an electronic switch or a laser or something like this, which has to generate this pulse sequence, which makes a digital gate. Now, what we say is actually, forget about this. No, why should you first translate a floating point number into a digital thing, then make an algorithm, and then translate this again to an analog signal? So we are basically trying to also merge this analog and digital ideas. So quantum computing has, I think, the huge opportunity to finally make analog computers cool again. And this is also something where quantum computing, I think, will play a huge role, that the data can be analog or digital.
Fantastic. I think the analogy with analog computers is really, really interesting, because it's somehow they got forgotten in the 30s. Somehow they got like left aside by the whole digital movement in the 50s and the 60s. And going back to that, I have one question, which is the following. You know, the big thing that broke that basically gave birth to the computer industry was, of course, the Entscheidung's problem and the papers and the work from Alonzo Church, Turing, and von Neumann, who basically made a thing that somehow responded and gave a practical utility to all of this. What is the breakthrough we are waiting for in terms of research? What is going on that you could say, well, if this research makes it and proves a certain theorem, this could actually bring could be a von Neumann moment, where all of a sudden we have things that could be built by a factory, and you could buy them even if expensive, and then maybe there would be some kind of economy of scale applying to that, so that prices would go down. I'm not speaking about the moment where they will reach consumer level, but what do you think? Is there like a breakthrough moment we are waiting for our own, I don't know, Kurt Gödel right now, thinking about the problem that if it is solved, we are going to move forward? Can you see that happening?
So I would say the Shor algorithm already was such a breakthrough, in the sense that it really showed that you can use quantum phases to exponentially speed up integer partition. So this I would indeed compare to the pioneering works in computer science. At the moment, I think we are more in this stage, which is more comparable to the question around Zuse and things like this, how to really build this. And I would say what is missing is the Bardeen paper about transistors. So this means, because this really led to miniaturization of chips, and this started somehow this hardware side. So I think what we are waiting for is somebody coming up with gates, couplers, or hardware designs which enable scalability of the architecture. And as we mentioned, without being humble here, we believe that, so to say, our architecture is more or less the only path to scalability, because we have these global gates, which allows one to design, on the other hand, completely new architectures.
So the old debate of what would be the successor to the von Neumann architecture could be the ParityQC architecture in that case.
Yeah.
Very good. Well, I seriously wish you the best, because I think it's thrilling. It's absolutely thrilling what you're doing. Yes.
So this is not really a joke. So we are serious about this, because
absolutely.
the von Neumann architecture, had this concept of memory, CPUs, and things like this. And in quantum computing, we have to go away from this, because there is no concept of memory. And the reason for that is that quantum information cannot be cloned. So quantum information cannot be copied. There is no copy. And this means that memory and CPU must be the same thing. So all the information has to be there all the time. By the way, another interesting analogy to computer science is that all gates are reversible. So that's another thing. Quantum computers will always be based on reversible gates. And there is no entropy generated during any computation that you're doing. And so there's many fundamental aspects about computing which have to be rethought.
Exactly.
And with our architecture, we have basically all these aspects of memory, CPU, and calculation inside our architecture.
So basically, the von Neumann bottleneck is gone. That's basically what you just said. I interpreted it.
So, for example, many people say that this could be one of the big issues for quantum computing, that gates are reversible and that don't produce heat, for example.
Wow. Well, there are no more open questions, and I think these final words are perfect for closing this webinar. I don't know if somebody would like to post a quick last-minute question. I don't see much activity in the chat. People are really happy. By the way, thank you so much. Jessica Wu saying, thank you so much for the great presentation. It's fascinating. It certainly is, Jessica. Thank you so much for attending. And if there are no more questions, I will thank you, Wolfgang and Magdalena. It's been amazing to have you and to learn about all of these things. I'm certainly going to go explore and learn a bit more. I have a few physics books in my shelves over there. We'll have to pick them up because I don't remember much from the little bit I've learned about it. So thank you so much once again. And thanks everyone for attending. I think it was a great event. Thanks for the questions, fantastic questions from the audience. And please subscribe to our channel, vision.tv. VSHN.tv. It's our YouTube channel. Please subscribe. We're going to be posting this video, of course, online, and feel free, of course, to ask any questions on the comment sections as well if you're watching this after we published it. Thanks again, Wolfgang. Thanks again, Magdalena. Thanks everyone from Exoscale as well. And see you around. And thank you so much. Bye-bye.
Bye-bye.